Hello students, in the previous video we have discussed about the DDA algorithm, that is the algorithm which is used for rasterization of line segments. In the same way we have one more algorithm for rasterization of line segments, that is the Bresenham's algorithm. Then why this algorithm is introduced is, in the DDA algorithm the DDA algorithm is easy to code, that means it is easy to write a pseudocode or an implementation of a DDA algorithm, but that algorithm requires a floating point addition. Where it requires floating point addition is, as you know, in DDA algorithm, to move from one vertex of a line segment to other vertex of a line segment, we will increment each time the x coordinate value by 1, and corresponding to x coordinate value we need to increment a y coordinate value. Increment in y coordinate value is nothing but adding a m value to a y coordinate value. As you know, m value is a floating point value. When we add m value to y coordinate value, it is nothing but a floating point addition. As you know, compared to integer calculations, floating point calculations require more amount of time. So to reduce the time which is required in floating point calculation, people had introduced with the Bresenham's algorithm. In Bresenham's algorithm, we are not performing any floating point calculations, or the calculation will be in terms of integers. Here also in Bresenham's algorithm, we'll assume that the slope of a line segment what we are going to display is always between 0 and 1, and it will not exceed 1. Now assume that here whatever the dotted lines we are observing over here, that is nothing but a grid. The grid consists of multiple pixels, that is the smaller rectangles what you are observing are nothing but the pixels in the frame buffer. Here we are able to see a line segment over here, but initially in application program we haven't specified a line segment directly. We will specify only the end points or vertices of a line segment. As an output, the graphic system will display a line segment between those two vertices. Now assume we are in between the rasterization process. That means we have already updated some of the intermediate pixels between the endpoints of a line segment. Assume we are at the position I plus j by 2 and I plus 1 by 2 and j plus 1 by 2. Assume that we are in the middle of a rasterization process. That means we have already updated some of the pixels between the endpoints of a line segment, and we have to update the remaining things. Assume we are at the pixel I plus 1 by 2 comma j plus 1 by 2. That means the first dot which is mentioned over there. Then now from that point we need to update the next pixel until we reach the second vertex of a line segment. Now in that case we have two options to update the next pixels, that is whether to update the pixel I plus 3 by 2 j plus 1 by 2 or I plus 3 by 2 j plus 3 by 2. Those two pixels are represented as again two dots in the next column. Assume that we are at a particular pixel, that is I plus 1 by 2 j plus 1 by 2, but now we need to update the remaining pixels until the next vertex of a line segment. Now to update the remaining pixels, that is the next pixels, we have two options over here in the next column, or it is in the next step, that is I plus 3 by 2 j plus 1 by 2 and I plus 3 by 2 j plus 3 by 2. Now to take a decision whether to update I plus 3 by 2 j plus 1 by 2 as a next pixel, or I plus 3 by 2 or j plus 3 by 2 as a next pixel, we'll consider a d value. That is what we have written over here in this diagram. The d value will be defined as d equal to b minus a, where a is the distance from the topmost pixel till the slope value or a line segment, and b is nothing but the distance between bottommost pixel till the line segment or slope value. Now by calculating d value, depending on the sign of d value, we are going to decide whether to update the above pixel or below pixel. If the d value is negative, then we'll come to know that the line segment will pass closer to a lower pixel, so we'll update the lower pixel with a foreground color. If the d value is positive, then we'll update the upper pixel, because the line segment will pass closer to an upper pixel with a background color. This is how we'll take a decision to update the intermediate pixels between two vertices of a line segment. Then this is regarding Brazenham's algorithm. So whenever d value is negative, we'll update the pixel I plus 3 by 2, j plus 1 by 2. Whenever d value is positive, we'll update the pixel I plus 3 by 2, j plus 3 by 2. Then till now we have discussed the rasterization of a line segment. Under that we have discussed DDA algorithm and a Brazenham's algorithm. Now we'll see what is nothing but a polygon rasterization. Polygon rasterization is nothing but, as an example, we'll consider a rectangle over here. To display a rectangle on an output window, as an input we'll specify 4 vertices. When we specify 4 vertices, once we execute a program, all the pixels within those 4 vertices will get filled with a foreground color, and we are able to observe rectangle on the output screen. Then how the graphic system is going to identify which pixels are inside the polygon and which pixels are outside the polygon? The identification of pixels inside the polygon and outside the polygon is nothing but polygon rasterization. Now to identify the pixels inside the polygon and outside the polygon, we have multiple approaches. So to test them, we'll call that approach as inside outside testing. Inside outside testing is nothing but testing the pixels to check whether they are inside the polygon or outside the polygon. If they are inside the polygon, we'll update it with a foreground color. If they are outside the polygon, we'll left out or leave it as the background color itself. The first approach which is available to perform inside outside testing is a odd even test. Then how to perform odd even test is to understand that here we are considering first a simple polygon, that is a rectangle. Then you select any pixel over here in a frame buffer. Assume there is a frame buffer which is present behind. So select any pixel in a frame buffer. From any pixel, draw a line segment from that pixel to infinity. If that line segment intersects or crosses odd number of edges before it reaches infinity, then we will say that the corresponding pixel is inside a polygon. I'll repeat, to understand odd even test, here we are going to consider a rectangle, that is a simple polygon. Now to understand odd even test, we need to select one random pixel in the frame buffer. So from that pixel, draw a line segment from that pixel to infinity. If that line segment crosses or intersects odd number of edges until it reaches infinity, then we will say that pixel is inside a polygon. In the same way, select any random pixel, draw a line segment from that pixel until infinity. If that line segment intersects or crosses even number of edges before it reaches infinity, then we'll say it is outside the polygon. Depending on that, here I have written two lines over here. That is, in the first line, we have selected a pixel inside the rectangle and we are drawing a line segment towards the right side, that is right side up to infinity. We can't write a line segment till infinity, so I have written line segment till some point, and when it reaches some point, that is where I have written odd, till that distance it has intersects with only one edge of a polygon, that is nothing but one edge of a polygon is nothing but odd number of edges. So whenever a line segment intersects odd number of edges, then it is nothing but the pixel is inside a polygon. So that pixel will get updated with a foreground color. In the same way, we have selected one more pixel and I had drawn a line segment from that pixel till infinity, that is towards left side up to some distance, that is till where I have written even. Then in that case, the line segment intersects with two edges of a polygon. So whenever a line segment intersects with even number of edges of a polygon, it indicates the corresponding pixel is outside the polygon and will leave that pixel with a background color itself without any updation. So this is regarding odd even test. This odd even test will work only for a simple polygon but not for a complex polygon. What will happen if we apply a odd even test for complex polygon is, for that we have considered one more bit complex polygon, that is a star like structure. Now we'll try to follow the same procedure or the process what we have discussed before. So here also inside a star like structure, select any point and draw a line segment up to infinity. If that line segment intersects odd number of edges of a polygon before reaching infinity, then we will say that the corresponding pixel is inside the polygon, otherwise it is outside the polygon. Now if we follow that procedure, if we take any pixels at the corners of a star like structure, then we will get a valid result because those pixels will be there inside a polygon. But if you consider a pixel in the center of, that means in the center position or center area of a star like structure, that is where we have written a point called P. If you draw a line segment from that point P up to infinity in any direction, that line segment intersects with two edges of a polygon. Whenever a line segment intersects with the two edges of a polygon or even number of edges of a polygon, as per the test, it says that pixel is outside the polygon. But with respect to this case, actually the P is inside a polygon and it need to get updated with a foreground color. That is, the corresponding pixel need to get updated with a foreground color. So here we are getting a wrong result. That is the reason odd even test is valid only for simple polygon but not for complex polygon. In this star like structure, if we select any pixel at the corner of a star like structure and if we draw a line segment, that line segment will intersect only odd number of edges, so we will get a valid result. That means the corresponding pixel is inside a polygon. But if we select a pixel in the center area of a polygon, that is a star like structure, and if we draw a line segment in any direction up to infinity, that line segment intersects two edges before reaches infinity. So the test says if a line segment intersects two edges or even number of edges before reaching infinity, then the corresponding pixel is outside the polygon. But in this case it is wrong because P is inside a polygon and the corresponding pixel need to get updated with a foreground color. So odd even test doesn't give valid result for complex polygon. Then what to do when we consider complex polygon for rasterization? For that we have a second approach that is known as winding number. Winding number is a second approach which is available to check the pixels whether they are inside the polygon or outside the polygon. Then how to perform this approach is, when we start with a winding number approach, select any starting point or starting vertex in a polygon. From that starting point, traverse all the edges of a polygon in any direction by marking with some marker. In a winding number approach, select any starting point in a polygon and from that starting point traverse all the edges of a polygon in any direction until we reach the same starting point once again. Whenever we traverse the polygon, mark it with some marker so that we can identify we have traversed in this direction. Start from a starting point, traverse all the edges of a polygon until we reach the same starting point once again. That is the first step we are supposed to do. After that, select any random point inside a polygon and then identify how many number of times the edges are encircled with it. That is nothing but its winding number. The first step is, by selecting a starting point, we need to traverse all the edges of a polygon until we reach the same starting point. Then how to calculate winding number for any point or pixel inside a polygon is, the winding number for this point is the number of times it is encircled by the edges of the polygon. So when you select any point in the center area of a polygon, that is where we have written P, that point is encircled by the edges of a polygon two times. So its winding number will become 2. If you select any vertex at the corner of a polygon, then those points will be encircled by edges of a polygon only once, so its winding number will become 1. So for all the possible points, the winding number will be either 1 or 2. So whenever the winding number is greater than 0, it indicates the corresponding point is inside a polygon, otherwise the corresponding point or pixel is outside the polygon. So whatever the disadvantage we have faced in the odd even test, that disadvantage we have removed over here. Even if we select a point in the center position of a polygon, we are able to identify that the corresponding point or pixel is inside inside a polygon. So how to check that is, for that we need to calculate a winding number. If the winding number is greater than 0, it indicates the corresponding point or polygon is inside the corresponding point or pixel is inside the polygon. So we need to update those pixels with a foreground color. If we get any pixel which is outside the polygon, then we need to left out with a background color itself. Then when we consider rasterization of concave polygon, as we know, when we want to apply clipping or rasterization for a concave polygon, we cannot apply it directly. Before that, we need to convert each concave polygon to a convex polygon. The process of converting concave polygon to convex polygon is known as tessellation operation. So to perform tessellation, in a GLU library, we have a built-in tessellator. Here there is a small pseudocode which is available to understand how exactly tessellation operation can be done. So in the first line, we have written a GLU tessellator. GLU tessellator is nothing but the object of a built-in class to perform a GLU tessellator operation. Here we are creating an pointer for GLU tessellator, and then we are calling a function called GLU new test. GLU new test will create a new object to perform tessellation operation, and it will return a pointer for a new object, and that pointer reference we are assigning to a my test pointer what we have created just now. Then the tessellation operation need to be performed on each vertex of a concave polygon. Before performing a tessellation operation on each vertex of a concave polygon, that code need to be enclosed between two functions. One is GLU test begin polygon, the other one is GLU test end polygon. For each function will pass for each one of these functions will pass the pointer what we have created before, that is my test. Apart from these two functions, we need to enclose the logic between even other set of function, that is GLU test begin counter and GLU test end counter. Even for GLU test begin counter will pass the same pointer, that is my test what we have created at the beginning. Then after that, by using a for loop, we'll traverse through all the vertices of a concave polygon starting from 0th vertex till n vertices. N vertices is a variable which will hold the number of vertices which is present in a concave polygon. Then to apply tessellation operation on each vertex of a concave polygon, we'll use a built-in function called glTestVertex, and once we apply a tessellation operation, the result will be stored in a pointer, that is my test, and vertex of I indicate a particular vertex of a concave polygon. Once we apply the tessellation operation on all the vertices of a concave polygon, it will get converted to either one convex polygon or a set of convex polygon. Then on each convex polygon, we can apply a rasterization operation either by using a RD1 test or by using a winding number approach.